This lesson is about multiplying rational expressions. Remember, rational expressions are just fractions. When you multiply two rational expressions, you follow the usual rules about multiplying two fractions. You multiply the numerators and you multiply the denominators. For example, consider a normal multiplication of fractions situation. 9/10 times 5/3. You could multiply the numerators, 9 times 5 is 45, multiply the denominators, 10 times 3 is 30, and then simplify your final fraction, 45/30. They're both divisible by 15, so 45 divided by 15 is 3, and 30 divided by 15 is 2, and you've simplified your fraction. However, it is often useful to cross-simplify fractions before you multiply them. In the previous example, you could have simplified the 9 with the 3, and simplified the 5 with the 10. So the 9 and 3 are both divisible by 3, so they become 3 and 1. The 10 and 5 are both divisible by 5, so they become 2 and 1. Now when you multiply straight across, the fraction is already simplified. This is delightful. The benefit of cross-simplifying is that you simplify the fractions before you multiply them, thus keeping your numbers and expressions smaller. You can also cross-simplify rational expressions with polynomials. Let's take a look. Let's multiply the following rational expressions. Notice that if you were to multiply straight across using FOIL, the answer would appear quite complex and not in simplified form. Namely, x plus 3 FOILed with x minus 5 gives you x squared minus 2x minus 15, and x minus 5 times x plus 1 FOILed gives x squared minus 4x minus 5. This is quite complex. Whoops, let's go back. However, by cross-simplifying first, the answer will already be fully simplified and you don't have to FOIL anything. In general, cross-simplifying polynomials means that anytime you have the same binomial in the numerator and in the denominator, you can cancel them out. Take a look. In this multiplication problem, I have an x minus 5 in the bottom and in the top, so I can cancel them, leaving me with the simple expression x plus 3 times x plus 1. Believe it or not, these two expressions will give you the same input-output on a factor table, provided you're using the numbers in the domain. Whenever you are multiplying rational expressions, you will want to look for opportunities to cross-simplify before you multiply. Here's another example. Multiply the following rational expressions. Wow, this is looking fairly complex. Nothing is factored, and none of these trinomials are the same. At first glance, this problem looks terribly complex, and it would be if you actually used the distributive property to fully multiply out the numerator and denominator. Fortunately, we are always going to try to cross-simplify our rational expressions before we multiply them. We do this by fully factoring each quadratic expression first. So take a look at x squared minus 3x minus 28. It can be simplified, factored, into x minus 7 times x plus 4. Next, fully factor x squared minus 3x minus 18. It can be rewritten as x plus 3, x minus 6. Next, factor x squared minus 1x minus 30. It's actually x plus 5x minus 6. Then simplify, that is, factor x squared minus 2x minus 35 into x plus 5x minus 7. I didn't show you all of my work in order to do all of this factoring. It does take a little bit of time, but in the end, you have this nice, fully factored expression. The benefit of this is that anything you see on top and bottom, you can cross-simplify. So, for instance, there's an x minus 7 here and over here. We can cancel them. There is an x minus 6 here and here. We can cancel them. And there are two x plus 5s. We can cancel them, leaving behind just x plus 4 over x plus 3. How delightful. Now it is clear that we can cancel many of these binomials. Again, cross-simplifying rational expressions of polynomials means that once you fully factor the numerator and denominator, you can cancel out any binomial that appears in both the numerator and denominator. Here are some practice problems. Multiply the following rational expressions by first factoring each trinomial and then cross-simplifying any binomials that you see in both the numerator and denominator. It will take a little bit of work to factor each of those trinomials, but once you do, you'll be able to cancel out any binomials that you see in both the top and bottom. Well worth the effort. When you're done, take a look at the next page to look at the answer key.